right. Hello, everyone. Let's do our lesson on the introduction to projectile motion. When we are looking at projectile motion, we can have objects that move up at angles, or we can have objects that start at a horizontal start and move downwards in a projectile. Still a projectile because we only have acceleration in the y direction. So let's start here by drawing out a situation where we have an object starting from rest or an object starting from a horizontal start. So we will make our object just a little ball here. Actually, just one second. Okay, so we have a ball that starts here from rest. So say a small amount of time passes, then that ball will fall a little bit, right? And then a little bit more time passes. Remember that we have a downwards acceleration of 9.8 meters per second squared. Therefore, after another, say, second, it will have fallen a little bit farther in that time interval because it's accelerating downwards. Okay, so after another second, we'll assume that it's fallen even farther because of that acceleration. And then so that would be after 1 second, 2 seconds, 3 seconds. After 4 seconds, it will have fallen the farthest. We'll put it just down there. And we have a nice visualization of an object accelerating downwards from rest. Now, say I introduce a spring here, or something of this sort. So we've got a spring that is going to induce horizontal motion into the ball. Well, as soon as that ball leaves that spring, it no longer has any sort of negative acceleration in the x direction. It only has that same acceleration in the y direction. So what you're going to notice is our x distances between our snapshots of the ball are not going to change in distance. However, there's going to be no difference between it falling from rest and it falling from a horizontal start. So our first iteration, our first picture or snapshot of the ball will have fallen one square, but let's say it moved 1, 2, 3, 4 squares horizontally, something like that. Now at our next snapshot, again, another 1, 2, 3, 4 to the right because there's no acceleration or negative acceleration, but the acceleration downwards does increase. So same exact motion falling in the y direction, but in the x direction, it is at a constant velocity. So our next snapshot, it will have fallen the same amount all the way down here, but the x direction will be the same amount as it was up here. So it'll be 1, 2, 3, 4. And finally, it will have fallen as far as it would have if it started from rest. However, it has the horizontal start to it. It has that horizontal constant velocity. Therefore, I need to count over 1, 2, 3, 4, and it will be down here like so. And what you'll see here is now you have a shape that resembles something of a curved line like that. And that right there is our projectile. That's projectile motion. Okay. So what we notice, the big takeaway here should be that in the x direction, there's no acceleration, but in the y direction, there is. So let's go over some important terms here. A projectile is an object with only the force of gravity acting on it. The reason why there's no acceleration or deceleration in the x direction is because we are ignoring air resistance. Okay, this is really important. We ignore air resistance. Now the trajectory is in our little purple that we have there. It's the path followed by the ball. Now in our case, it just started from up here. So it starts from a horizontal start. And the range is this distance from the horizontal distance covered by the projectile. So right here to right here, that is our range. That is our range. So it's the horizontal distance covered by the projectile. A couple more properties that are important to know. The motion in the x direction and y direction are always going to be independent of one another. So never combine the x and y directions in calculations. Always keep them separate. So like I said that I'm always going to be saying, treat your x and y components separate. Okay? So they're always, always, always going to be separate of one another. Okay? Not together. So I guess I could write here, they are not going to be equal. Don't put them together. Now, the horizontal velocity, Vx, stays the same at all times because there's no acceleration in the x direction. So anytime you are asked to solve for the x velocity, you assume no acceleration. And when there's no acceleration, our formulas that we can use become very simple. If there's no acceleration, well, that means that our velocity is constant. So therefore, it's just delta d over delta t. That's the only part. And I put little subscripts of x there because it's only in the x direction that is true. Now, here is your key. I like to call this the key to solving projectile problems. This is very important. Time is your key between x and y. If I can find time in the x direction, that time that's passed is going to be the same in the y direction. Okay, so time is the key between x and y. It's the link. Okay, so the x and y link is time. I don't know if that helps you or not, but just a couple visuals. Now, a couple hints besides using time. Divide the projectile motion into two problems, the x direction and the y direction. I basically already said that. Treat the y direction like any sort of question you've ever seen where the object is moving straight up or straight down under only the force of gravity. And remember that acceleration is always 9.8 meters per second squared down. So every time you're thinking about the x direction, or sorry, the y direction, always just think about it as going up and down. This will make your life a lot easier. Because then the x direction is just like I said up here, it's a constant velocity problem. There's no acceleration. So we're only looking at the x direction as a constant velocity. The x direction and y direction are connected through time. Very important, connected through time. This is going to be a helpful step in solving problems because you can calculate the time using one direction and then you automatically have time in the other direction. So if I've only given you x displacement and x velocity, or even just the initial velocity in the x direction, well, then you can solve for time, and then all of a sudden you have a bunch of info to be able to solve the y direction. You know the y direction initial velocity is going to be 0 because it's starting from only a horizontal start. So y initial velocity is 0, y acceleration is 9.8 meters per second squared down, and then you've found the time from doing the x component. Well, now all of a sudden you have three things. Now you just need to find the fourth, and the fourth will either be finding the final velocity in the y direction, or it will be finding the displacement in the y direction. And in both cases, now all of a sudden your life is a lot easier if you know time. Let's do an example together and then we'll be done for today's lesson of notes. So, an airplane is flying in a horizontal direction at 125 meters per second and an altitude of 1,250 meters. The airplane then drops a package. How fast is that package falling vertically when it strikes the ground? So how fast is it falling vertically? So basically what the question is asking us here is what is the final velocity in the y direction, right? How fast is it falling vertically? Now let's do the same thing that we always do. I'm going to set up a positive direction and a negative direction. In this case, because it's falling and it's starting from rest, I'm going to make down positive and up negative. It's never going to be going up. So now it's nice. We can just deal with positive numbers. So the altitude here is our displacement in the y direction. The altitude is 1,250 meters down. I'm just going to be using that symbol instead of writing down. Now the next thing that we need is we're trying to find how fast it's falling vertically when it strikes the ground. So we're actually not concerned with the horizontal direction. We could write down what it is, right? This right here, it's flying in a horizontal direction. That's our x velocity. Not going to be useful to us for the first part here. 125 meters per second. And we can say it doesn't really tell us which direction it's going in, but it doesn't really matter. We can say that it's going this way and that's positive. So what else do we need? What else do we get from this question? Well, we know that it's falling, right? So that means that its acceleration due to gravity is going to be 9.8 meters per second squared down, okay? And it is, where does it say? Dropped. It then drops a package. So it's dropped from the plane. So what's its initial y velocity? That's another hidden piece of information. It's 0, right? Because if you drop something, it starts initially from rest in the y direction. So let's use the proper formula here to be able to find v2y. Now don't get intimidated by the fact that there's y's in there now. These formulas don't change. Just imagine that there's little y subscripts all over the place. So v2y squared equals v1y squared plus 2a delta dy. So let's write it down. v2y squared equals v1y squared plus 2a delta dy. And very nice, we have got a 0 here, right? Our v1y is 0, so that can cancel out. And now all we need to do is take the square root of both sides, right? If we take the square root of both sides, that's how we can isolate for v2y. We want to get that square out of there. So the opposite of the square is doing the square root. So v2, now I'm going to switch over to my scalar values. Remember, down is positive. So I have the square root of, that's obviously 0, so we don't need to include it, 2 times 9.8 meters per second squared down. So it's a positive number, we just leave it as is, times delta d, which is also down, so also a positive number, so we just leave it as is. And we get the square root of 2 times 9.8 times 1,250, and we should get 157 meters per second down. Let's write it out properly here because it's a positive number, so we know it's down. V2y is equal to. So there we go. There you have it. Basically could have done this question without being told at all what the what the initial x direction or x velocity was, right? So in this case, we just treated it like it was an object dropping, basically. Now, how long will it take? Well, it's not really anything more tricky or something that we haven't seen. We just need to now take all these and solve for t. So now instead of using this formula, I'm going to use this formula. V2 equals V1 plus A delta T. But now, instead of just writing it out as V2, I'm going to write it out as V2Y equals V1Y plus A delta T. Now, I don't need to put a delta Ty or anything like that because remember, the T is the same in the X and the Y direction. So, and I also don't put the Y by the A because I'm assuming we already know that there's only acceleration in the Y direction as well. So again, V1Y is 0. So this is really nice. This is 0. Now I'm just solving for delta T. So delta T is equal to V2Y divided by A. I just divided by the A on the other side. And we know what V2Y is now. It's 157. Now, I rounded my answer here, and this is something that I should have mentioned before. When I actually calculated my V2Y, when I plug it in my calculator, it actually isn't 157 exactly. It's 156.5 meters per second. Okay, it's 156.5 meters per second down. Now, this is important. Don't use your rounded answer for a part B in a question because it will change how accurate your time answer is. It'll change how well it's rounded. So what we need to do is use our 156.5 instead of 157 and our 9.8 meters per second squared down. And we will get that delta T is equal to, if I calculate this, plug this into my calculator, I'll get 16.0 seconds. 16.0 seconds. Now, what does our part C ask? What is the actual velocity when the package hits the ground? So now we need to combine our X and Y components. So we know actual velocity basically just means give me the full angle, right? And the hypotenuse. We're using the angle velocity. So I've got 125 meters per second to the right or forward. And then we calculated that it was 157 or 156.5. Let's use that. 156.5 meters per second down. So now our last thing that we need to find is we need to turn this into, basically what we're doing is we're doing like what we had done with the components of vectors. We need to combine the X and Y components and find the resultant, which the resultant is going to just be the final velocity. No X or Y, note that, right? It's the final velocity and theta, which is the angle. So doing this again, this is nothing new that we haven't seen before. Okay, I'm going to pause this right now and I'll come back to it in a couple seconds. I'm just going to keep giving my video lesson here, so you're just going to have to listen to me just for 1 second. So we combine our X and Y components using Pythagorean theorem to find that V2. So we take, we got A squared plus B squared equals C squared. So we take 125 squared plus 156.5 squared, and then we take the square root of those two, and that will give us, let's plug it into our calculators. So 125 squared plus 156.5 squared, and then the square root of that should give us 200.2, 200.29. So 200.29, let's go with 200.3 meters per second. And then to find our angle, we have to use the inverse tangent of the opposite over the adjacent. So the opposite, we have 156.5 over the adjacent, which is 125. And that, my calculator, inverse 10, we get 51.4 degrees. I'm almost finished here, just one sec. So 51.4 degrees. So our final velocity is going to be, if I take a look at what is my, that's basically, I've made it impossible to write this as proper sig fig, so we'll have to put a bracket after, but let's go 200 meters per second, and then we'll label this as 51.4 degrees below the horizontal. I did not leave myself enough room there. That's okay. And then we'll say 3 sig fig. That's a long answer, but that is technically how we should write it out. Our last step here before we're finished is that we need to calculate the horizontal displacement. And if we do the horizontal displacement, remember that Vx is constant. So Vx, there's no acceleration. And the time is the key between the two of them. The time is the same in the X and the Y directions. We calculated it to be 16 seconds. Therefore, we have a really straightforward question here. Delta dx is equal to what? So we are just rearranging that. One of the first formulas we ever learned in physics, Vx equals delta dx over delta t. And therefore, if I solve for delta dx, we get Vx times delta d, which is 125 times 16. So delta dx is equal to, if I plug that in, I should get 2,000 meters. And if I want to write that with the proper sig figs, we can convert it to scientific notation, 2.00 times 10 to the 3 meters, and we'll say in the positive direction. I'm running out of room. It's the positive direction. So there is our final answer. Right there. I kind of ran out of room at the bottom, but you get the idea. All right, we'll talk to you at the next lesson.